Hi, and welcome to MSc. In this video, we're going to be looking at adding and subtracting radicals. So to fully understand how to add or subtract radicals, we should look back at thinking about adding and subtracting like terms. So if you remember back to the beginning of your algebra days, you might have seen questions like this that would say 2x, whatever x represented, plus 6x, for example, and you'd get 8x. You'd have 8 of them, right? 2 apples plus 6 apples is 8 apples. You might have also seen questions where it was x squared, and maybe you would have pictured like a square shape as opposed to a long, narrow shape for x. And if you had 3x squared plus 4x squared, well, those are like terms because they have the same variable raised to the same exponent, and you'd say, well, I have 7x squared. But you would hopefully remember learning if I had 2x plus 3x squared, well, those aren't the same. X and x squared are not alike, so there's no simplification I can do. Similarly, if I had different variables, 2x plus 7y, again, those are unlike variables. I can't add those. So we have very similar ideas here to all this like term algebra that you already know. So similarly here, we can only add radicals when they have like radicands. And again, the radicand, if you remember, is the value under the radical symbol. If you haven't watched my video about radicals and simplifying radicals, you should go check that out and come back here when you're done. Because these do not have like radicals, and as it turns out, there's nothing I can do to simplify these. I cannot add these. This would be just like having an x and a y, or an x squared and an x. I can't add them. Nothing I can do with this one. It will just stay as square root of 5 plus the square root of 3. There would be a decimal equivalent, but this would be an exact answer, whereas the decimal equivalent would be a rounded value. Over here, however, I see I have a root 3 plus 4 root 3. Well, these are likes, right? It's like radicands, they're the same number. When there's no coefficient, just like if it was an x, there'd be a coefficient of 1. So we have 1 root 3 plus 4 root 3. So in that case, we can say, well, I have a total of 5 root 3's. Notice that this is just like adding the algebraic expressions that we've had before. Right? If this was x plus 4x, we would call that 5x. And again, we don't do anything with the x values, that x factor. It's still just x, whatever that represents. Here we don't add what's under the radical symbol. It is still root 3. I'm counting how many root 3's I have. I have 1 plus another 4. So just like the x didn't change when we added like terms, the radicand does not change when we add radicals. So on the surface, this might look like it's exactly the same as adding like terms. Let's consider this example or this situation here to further explore what's actually going on. So if I tried to add these shapes to come out with an answer, you might look at this and say, well, this can't be done, right? This is like an x and a y. I can't add those. All my answer would just be, it would be x plus y. There's not much I can do. And from a variable standpoint, it would be totally correct, right? These are different shapes. I can't add them. They're not alike. However, sometimes we can simplify one or both, maybe, of the radicals so that addition or subtraction is possible. So am I saying we can add these? Well, in a way, yeah. If we picture these as radicals that maybe I could simplify, I could picture dividing this up and saying, well, that's actually 2 of those triangles. And if I did this, well, there'd be another one of those triangles, and then another 2 as well. So if I were to add these together now, you'd actually say that there would be 1, 2, 3, 4, 5 of those triangles. And so that's different than the algebra we've done with just variables, x and y and x squared. So how does this relate to radicals then? So let's consider an example here. If I had this term being, let's make it the square root of 28. And this one, for example, will be represented by the square root of 63. Again, at first pass, one's a square and one's a different shape that's not a square, right? It's a trapezoid. And so we have the situation that can't be added. But I know with radicals, I can simplify. I'm looking for that perfect square underneath, right? So I can actually write this as root 4 root 7, which will be 2 root 7. And over here, I can rewrite 63 as 9 times 7. And this will then give me 3 root 7. And so the total here of these, my format here is probably not perfect with equal signs the way I have it set up. But as an example, you understand here that now what we have is the 3 root 7 plus the 2 root 7, which would be my 5 root 7. So we can understand that because unlike x's and y's, I can actually break down radicals to simplest form. What that allows me to do is it allows me to simplify these and potentially add ones that at first pass don't look alike. I think for better format purposes, I should get rid of those equal signs there, right? We have 28, root 28 plus root 63. We've simplified it fully, and now we get an answer, right? And so if the triangles were root 7, that's what we've done. So let's look at a couple examples where we'll apply this. So we're looking for simplification of the radicals. Well, there's nothing I can do with this first radical. So now I look at the second one. I'm going to keep my coefficient of 4. Well, this root 12 can actually be rewritten as 4 times 3. So root 4 times root 3 is root 12. And so this will be 7 root 3 minus 4 times 2, because the square root of 4 is 2, root 3, and I'll show all my work here for the clarity of this video. Right? 4 times 2 is 8, 7 minus 8, this is going to give me negative 1, and I don't have to write that coefficient of 1, it's going to give me negative root 3, or negative 1 root 3. So I was able to simplify this 12. Didn't look the same as the 3 initially, but I was able to make them look the same and then do some simplification. Sometimes I'll get a situation where I can simplify one, but it doesn't simplify to the exact same radical. So all I can do is simplify it. I can't actually add or subtract them. So watch for trickier examples like that. Although most of the time examples that are built like this, you'll be able to simplify down to the same radicand and add the radicals. Moving over to this example, we'll see here that actually I can simplify both of these. So this 18, I'm looking for a perfect square that can go into it. Well, 9 can go into that, and that would be 9 times 2 is 18. And now I have the 50. So the 50, well, 25 times 2 is 50. And I chose that instead of 10 times 5 because 10 and 5 are not perfect squares. So that's not going to help me. Plus this root 2 and that root 2 will hopefully generate like radicals at the end. So this is going to be 2 times 3, root 2, plus 4 times 5, which is the square root of 25, root 2. And this will be 6, root 2, plus 20, root 2. And this would give me 26 root 2. Okay, so that is how we add and subtract radicals. We can only do it when they have like radicands, but unlike regular algebra with x's and x squareds and y's, we can actually do some simplification to the radicals with the hopes of generating like radicals that we can add or subtract. Thank you for watching this short video. I hope you found it helpful. If you have, consider to like and subscribe, please. And thank you for listening.